Let's talk about autonomous driving, and then especially let's talk about how to make it affordable. And then we start with a crash course on autonomous driving. What is autonomous driving? What kind of technology are we using for autonomous driving? Then why is it so expensive today? And then how do we make it affordable? So that's the flow. And then at the end, we have a demo. We have a video demo for that. So first of all, what's autonomous driving? People often misunderstand that saying that autonomous driving is one technology, but not. It's a bunch of technology you need to integrate. So let's look at this overview of the technology step for autonomous driving. We have the pink part, and that's the algorithm. First of all, we have sensing. How do you get data from the environment? So just capture the data. You have GPS IMU for localization. You have LiDAR for localization, obstacle avoidance, and then you have camera for perception and so on. And then after sensing, you get the data. Then the next step is to understand the data. That's what we call the perception step. We have localization. Now you have your sensor raw data. How do you process that to derive the current location of the car? And then object recognition. You see a lot of stuff on the road. For example, pedestrians. You want to avoid those. And then object tracking. You want to predict the trajectory of other cars and predict the trajectory of pedestrian. At the end, it's the brain, the actual brain of the autonomous driving pipeline. We have path planning. How do you plan your path? And then how do you do action prediction of other obstacles and vehicles? And then how do you avoid those vehicles? So these are just the algorithms. There are a lot of algorithms involved. And then if you just have the algorithm, you cannot build a car with just the algorithms. You need a hardware platform to bind everything together. How do we implement all these algorithms within a small computer that can fit into the car? So we have the blue part, which is the client system. And then on the right side, on the right side, you have this cloud platform. So when we talk about autonomous driving, often we talk about the client devices. But there's a huge cloud platform behind actual autonomous driving. For one thing, you need to build the map, the high definition map. How do we build that on the cloud? You need to do simulations. You need to do model trainings for your networks. And at the end, you have a huge amount of data to store. Just to give you an idea, for a autonomous vehicle like this, at its peak, each second it can generate 2 gigabytes of data. So we need a huge storage infrastructure just for autonomous driving. So next, let's go over these components one by one and then see what are the challenges and then why is it so expensive today. First of all, localization. The most crucial task in autonomous driving, to me, is to know where your vehicle is at any moment of time. So when you talk about localization, the first thing you can think of is GPS. Well, when you drive, you use GPS. Say you have an iPhone, you have a $3 GPS inside it. In a very clear environment, you have 1 meter by 1 meter or 1 meter radius accuracy. So you can bound the area of localization within 1 meter. But then if you are driving it within San Francisco, then the area goes up to 20 meters because multi-path problem and some other problems. So that's not good enough for autonomous vehicles. For human-driven cars, it's fine because you can correct the area. So there's the second generation of GPS, which is called RTK. The theory behind is that we know if we get a signal through the atmosphere, there might be some interference and some noise in the signal. That's why you have the inaccuracy in localization. But if you could deploy some base stations around you, and then each base station will broadcast this air correction signal, then with the correction signal, you can get to a centimeter level accuracy. But the problem with this approach is that, first of all, you need to deploy these base stations. It's very expensive. And then each base station will cover a very small area, 10 to 20 miles. And then on top of that, it's very expensive to get a receiver for that. But then the good news is that there's a third generation of GPS, which we'll call PPP. The PPP GPS system would be launched in 2018 and so on. The basic theory behind it is that you have several huge base stations across the continent, several these base stations for each continent, and then they combine their signal and broadcast their correction signal through the internet, and then you get it to achieve a decimeter level accuracy. But the problem with PPP, there's several problems. First one is it's not ready. The infrastructure is not ready. The second problem with that is that there's very long warm-up time. It takes about 30 minutes to warm up before you can use it. But with GPS alone, you can achieve about decimeter or even centimeter level accuracy. But we cannot just rely on GPS technology for localization because sometimes you don't have signal. You're in a tunnel or something. So second and the most popular means for localization today is LiDAR, or the laser ranging device. But it works with the high definition map. We will talk about the HD map later. But LiDAR is basically emits a beam of laser, and then it measures how much time it takes to travel back. And then by measuring that time, you can derive the depth of the point in space, what we call the point cloud. And then on top of that, you get something called the reflectance value. If you shoot a beam of light on a wood or against a metal, you get different values. That's just very similar to feature points in, or feature descriptors in computer vision. And then you have captured this environment with all this reflectance value and then depth information. Then you can construct what we call the high definition map. By comparing what you capture at the moment against a map, then you can kind of localize where you're at. The technique behind is called particle filter, if you want to dig deeper. But let's look at, spend a little bit of time looking at HD map. How is it different from Google Map, for example? Google Map is a grid map based on satellite images. So its best resolution, it gives you 1 meter by 1 meter resolution. It's a grid. But then if you have 1 meter resolution and then you try to drive a car and then have the car drive itself on the road, that's not enough because it's not lane level accuracy. So on Google Map, it gives you a road level accuracy. Say you can go to San Francisco and say, it tells you from point A at Main Street, go to the point B on Main Street. But that's enough, right? That's enough for you to drive. But for a vehicle to drive itself, it needs to know which lane it travels on. So to get to lane level, you need decimeter level or 10 centimeter at least accuracy to achieve that. And then LiDAR, why is it so popular? Because it achieves that. It gives you 5 centimeter by 5 centimeter resolution. It generates the 2D grid. So the way it works, it's like a cake. You build layer by layer. The bottom layer, you have the laser to scan the whole environment to give you this 5 centimeter by 5 centimeter grid. On top of it, you have a second layer called reference line. You put a reference line to give the direction of the road that you are traveling. Then on top of it, you give one more layer, the lane layer. It tells you this part is lane 1, that part is lane 2, and so on. Then on top of it, you have semantic information, such as speed limit. And then even on top of semantic information, you can put commercial information. Say that's a KFC and that's a McDonald's. That's how we build the HD map. There are 3 requirements down there when we build HD map. The first one is fresh. This one is very important. If you use Google Map, it updates once every 6 months or longer. Depends on where you're at. But for HD map, the basic requirements weekly update for the reason that if one lane is blocked, you need to update your map to reflect that. Otherwise, if your vehicle depends only on the HD map, it will crash. So weekly update, that's a strong requirement. The second one needs to be very precise, 5 centimeter by 5 centimeter. The third requirement is if you put this map infrastructure in the car, it needs to work very well with your client devices. So there's one startup out there, it's called DeepMap. They have the best technology so far for building this infrastructure. Welcome to check it out. Well, the standard requirement is weekly. You may need more than that. The industrial trend is crowdsourcing. Say if every car is equipped with a LiDAR, then you may get a real-time update. But we'll see how that happens because LiDAR is very expensive, as we will discuss later. DeepMap. So next, well, do you have to use LiDAR for localization? Not quite. If you have good technology, you can use computer vision. So this is how it works, basically. Let's take the basic version. It's called stereo visual odometry. You have 2 cameras, left and right, just like you have 2 eyes. And then these 2 cameras go into this pipeline triangulation to derive this spatial information or the depth of each point in space. Then you create this disparity map. So now you have a disparity map. Then you move forward by one frame. You get two images again. You get another disparity map. Then you compare these two maps. Say, hey, these pixels were here. Then now they're here. By having this information, you know the car or the vehicle has moved, say, 5 meters. That's how you know your translation or your movement, by using visual information. There's a different flavor of visual odometry. It's called mono, using single camera. But that's really hard to do. That means you have one camera, so you don't have the depth information. That means you have to do a very good initialization. At the first frame, you need to establish your ground truth. So what are the spatial points you have? So that's very hard to do. The third type is called visual inertial odometry. The motivation behind is that cameras are not fast enough, especially when your vehicle is traveling at 60 miles per hour. But then if you have a frame rate of 20 frames, then it's not going to be enough. Why not use IMU? IMU is a very fast sensor, though it's not very accurate. So they complement each other. One is very accurate but slow. One is very fast but less accurate. So that's visual inertial odometry. The next type of localization techniques called wheel odometry. You can count how many rounds the wheel has rotated. Then you can derive the distance you have traveled. So that's wheel odometry. There's several popular type Ackerman steering. That's most popular for vehicles. Differential drive, that's most popular for robots. Tricycle, that's another popular one for a vehicle. So that's a short introduction for localization. Then let's talk about perception. Perception today mostly is vision-based, so you use computer vision to perform several tasks. The first one is detection. So if you are driving, you have the car drive itself, someone is standing in front of it, you want to detect it. The question becomes what kind of model you want to use. You don't want to use a huge model, the ones that have, say, 120 layers. That's too slow. So we want a fast model, yet it gives you enough accuracy. So two models stand out. The first one is faster RCNN. It obtains what we call the ROI, the region of interest. Then you try to classify the region of interest in two steps. One step is step one, to find out what are the ROIs. Step two, to classify. So it's called faster RCNN, but it's not fast enough. So there's another technique called SSD, single shot multi-box. So it does this ROI obtainment and classification in one step. That's why it's faster. But both are working very well in the scenarios of autonomous driving. Semantic. So you have a very complex scene. You want to understand these are the road, those are the pedestrian, those are the trees. So you need to do a semantic segmentation of the scene. So the network that's most popular is called PSP. It basically tries to break the scene into different pixel groups and then group the pixels together. Say, hey, these pixels are the road and those are the pedestrian and so on. So PSPNet is very popular for segmentation problems. Stereo block matching. So at the beginning, we talk about visual odometry, stereo visual odometry. You want to derive the depth information from vision information. The traditional technique, if you check out the OpenCV website, it's called semi-global block matching. That's the most popular one in the computer vision world. But then there's a network for that as well. It's called content CNN. Basically, it has the same network for the left image and the right image. Then they go through the same inference step, and then at the end you combine the two to produce output. The output is the depth of the points in space. So by using content CNN, you can improve the accuracy of SGBM by 50%. But then it's very expensive. You don't want to put it in the car. Or maybe you don't have enough computation power to perform this in the car. It's very computation demanding. And then if you know about computer vision, there's some technique called optical flow to track the movement of objects. In 3D, it's called scene flow. Traditionally, we use geometric techniques, which is optical flow. But then now we have a network for it called FlowNet. But it suffers from the same problem. When you use CNN like this, it's very computation intensive. So I'm not sure whether you can put all these networks in the car and perform all these tasks. Again, so that's the very short introduction of perception. Then let's talk about the brain of the vehicle. The planning and control is very complicated. So if you think convolution neural network is complicated enough, this one is more complex. So that's the whole very, very high-level architecture of planning and control. So you have two input, perception and localization. Perception gives you what are the objects that are detected, and then localization gives you the current location of the vehicle. Then it goes through two steps. The first one is prediction. So if you detect a person in front of you, next thing you want to do is to predict what is this person's next location so that you don't want to hit him. And then routing. Routing, you take the localization information and then you plan a route such that you can go from point A to point B. So these two modules output their routes and trajectory to the core, which is in the red box, the core modules of planning and control. Behavior planning or behavior decision, motion planning, and feedback control. Mostly motion planning and feedback control, the expertise are owned by the vehicle manufacturers, whereas behavioral decisions are mostly done by researchers in internet companies, say Google, Baidu, Waymo, and so on. So action prediction. What is action prediction? So say you have a car, that's your car, you want to turn left. On the other side, there's another car coming forward. You want to predict whether this car is going forward or turn right, so that you can plan your action accordingly. Similarly, you have traffic prediction. And there are two kinds of traffic prediction. So you see there's a pedestrian, maybe he's crossing the street, but you don't know. You want a probability of him crossing the street or not. So the first kind of model is classification. It just tells you whether this guy is going to cross the street or he's not going to cross the street. So that's fairly easy. The harder one is regression. So if this guy were crossing the street, what's the speed that he's crossing the street? You want to calculate that such that you can plan your action to go around this guy instead of hitting him. So that's a prediction module. Routing. Routing is quite different from what we have today, because what we have today is road level routing, whereas what we have here for autonomous driving is lane level routing. But it's similar algorithm, Dijkstra's and A star. So what we do is to break the road into many lanelets or small segment of lanes. And then when we do routing, we say, hey, which lane should connect to which lane? And then you can derive the shortest path from point A to point B. So that's basically how it works. So if you look at the red part here, you have lane 1 connected to lane 2, lane 3, and so on. That's your output. That's your routing output. You give this lane output to the next module, which is behavioral decisions. So how do we do behavioral decisions? It's very complicated. What took Waymo many years to develop is actually a set of rules. They have several thousand of rules to do behavioral decisions. So we kind of group these rules into different scenarios. The first scenario is master vehicles. That's your vehicle, what your vehicle is going to do. There's some limitation and some rules apply to your vehicle. Second scenario is the front vehicle scenario. So if there is a car in front of you, what do you do to it? So there's second kind of scenario, and so on and so forth. You have like 30, 40 scenarios combined together. And then each one applies some limitations to how you can maneuver your car. So after you go through all these decisions using a Markov decision process, then you derive a group of consolidated, what we call the synthesized decision. Then that's what you pass to the next guy. The next guy is the control system. The control system will take these decisions and tell the car what to do next. So, all right, very briefly, we went over all the algorithm elements. Then let's talk a little bit about the hardware system itself. So what kind of hardware we need to make this happen? So a typical architecture is like that, 3 parts. The first part is the sensors, LiDAR, GPS, camera, and so on. You have all these sensors connected to your main computing engine through PCI or Ethernet connections, mostly PCI for speed reasons. And then there's I/O switch to route this data to your compute box. We'll talk about compute box later, but it's very expensive. Usually it contains a very high-end CPU, say Intel Xeon or Intel Core i7, then several NVIDIA cards for convolution tasks. Then after your computing step are done, then you have something called the CAN bus, which is the control network. Then you send all the commands, you dump all the commands to the CAN bus to control your vehicle. So that's the basic architecture. But in reality, what happens is this. You have a high-end CPU plus 8 to 16 GPU cards, 60 teraflops per second. At its peak, 3,000 watts. That's very crazy. If you look at the mere cost of it, it's $20,000 to $30,000 to just build this compute engine. But it's getting cheaper and cheaper as people roll out more design and so on. But due to the heat dissipation, often you don't see on the autonomous vehicles, at the bottom of it is a huge fan to help heat dissipation. In first generation, they put it in the back seat so that you don't never see someone sitting in the back seat in the first generation. Second generation, they put it in the trunk and a huge fan below for heat dissipation. So, affordability. My personal belief is that if the cost of your autonomous vehicle is $200,000 to $300,000, I cannot afford it. I doubt many people can afford it. So if you want to ship this kind of car, you want to use affordable hardware, yet reliable. To make it affordable, we try to examine why is it so expensive today. Let's look at the cost breakdown of the components and so on. So Baidu recently announced their Apollo project. They open sourced their hardware spec. So if you go through their hardware spec, you see all this hardware. First one is Velodyne 64-line high-end LiDAR. On the market, it's $80,000 per piece. $80,000, one piece of LiDAR. And then for the high-end GPS receiver, the RTK receiver, it's about $10,000. So if you just count the sensors alone, it's roughly $100,000 already. Then if you look at computing solutions, that's NVIDIA PX2. The Drive PX2, it's around $10,000 a piece. But then if you build a solution around it, it's more expensive. It's around $20,000, $30,000 to just build a computing solution. But the most expensive part is the map. Minimum requirement, weekly update. Imagine you run an operation, you equip with a very high-end vehicle, let's say $500,000 per vehicle. You run the vehicle around the streets of San Francisco per week. And then you try to build this pipeline in the back end to construct a map. And then you, over the air, OTA, you push the map back to the car. So that's the infrastructure requirement. So if we zoom into the map, if you look at this figure, it captures raw data. From the raw data, it derives these point counts, or the spatial points. Then the spatial points, you need to connect the points, stitch the points together to make it into a map. That's your raw map. Then you kind of squeeze the 3D map into 2D, so you just capture the ground. You don't capture any noise, say pedestrian and so on. And then you put the reflectance value, like we discussed in the beginning, there's a reflectance value for each point. You put that on top, and then later on you do the labeling and so on, semantic information. That's why it's so expensive. It's millions of US dollars to capture and create a map for a city like not even San Francisco. To maintain this map for San Francisco, probably millions of dollars a year. So who's going to pay for it? Can we keep the question to the end? Thank you. So the question becomes, how do we make it affordable if we look at each of these components? First of all, can we use computer vision to reduce the cost such that we don't have to use LiDAR? Second of all, what kind of computing hardware is required if we switch to computer vision? Third of all, what kind of map is required? Or what kind of map can we build with just computer vision? So that's our product from Perception. We built this, what we call the Dragonfly product, and then we try to solve this problem. So the product has 4 cameras. If you look at the shape of it, it has 4 cameras. I'll tell you why it has 4 cameras. It's very interesting. So 2 cameras in front, 2 in the back, so that you have a 360 view of the environment. What does that mean? 360 view of the environment. What it means is that if you have a single camera, you raised the question, if you have a single camera, put it on a car, would it work? Well, if I take a shot here, right, that I see you. But then if I make a turn just like that, I take another shot and I don't see you at all. There's no overlap at all. If 2 images, they have no overlap, you cannot track the vehicle. That's the main problem we face today. But if you have a 360-degree camera, no matter how you turn, you never lose track of the vehicle. Okay, that explains the front and back part. Why do we put 2 cameras in the front? Because you can derive depth information, spatial information. If you have 1 camera, you cannot derive spatial information. And then why do we have a base like that, 50 centimeters? That's because we want to cover a range of 50 meters or more to start with. So that's the basic design. And for the whole pipeline is actually sensor fusion. With camera alone, you cannot do reliable localization. You cannot do a lot of things. So we have a basic GPS pipeline combined with IMU that gives you an initial location of the car. Maybe there's air with it that's, say, 10-meter radius. Then on top of that, you have the wheel. The wheel actually help you to correct the error of the GPS. Then on top of the wheel, we have this. We have what we call the visual odometry pipeline to help localization. So that's the sensor part. By making this, it's already much cheaper. Second part, we did a very interesting experiment about more than 1 year ago. The question we asked ourselves is that if I had a computer vision-based autonomous driving workload, and then if I put this thing onto a mobile device, say my cell phone that's running on Qualcomm chips, how well would this work? So the first step is to understand what's on this cell phone. We have a 4-core ARM CPU, we have a DSP, and we have a GPU, not much resources. And at its peak, it burns about 15 watts of power. Remember, when we look at the real implementation on car, it's 3,000 watts. So the next step is to figure out what kind of workload fits what kind of chip for heterogeneous computing. Well, when you talk about computer vision, there are actually 2 workloads you care about. The first one is localization, or the traditional computer vision techniques that involves feature extraction and so on. The second one is convolution, or the CNN pipeline. And then through our study, we found out that if you do computer vision techniques, such as visual odometry, DSP is the best fit in terms of power consumption, in terms of performance. And then if you do convolution kind of workload, say CNN, content CNN, and so on, GPU is the best fit. I think that's very well known by now. And then CPU is very good at control. So it becomes the matter how we divide the workload onto different part of the chip to make it work. So this is our architecture. We have DSP for sensor data processing to extract features. Then the features go into the main pipeline. We have 2 threads, or 2 CPU threads for localization backend. And then we have a GPU for object recognition. Then we feed the output to planning and control. We leave 2 CPU threads for their planning, obstacle avoidance. Then it turns out the performance is not bad at all, even on the cell phone. For localization, it's able to process 25 frames per second. For object recognition, 3 frames per second. Kind of slow, but still works. 11 watts. We were able to drive a small vehicle at 5 miles per hour with this simple chip. So wow. So if we give it a little bit bigger chip, then it can handle much better workload. So that's what we use. We use NVIDIA Jetson series of chips that help us to bump the speed up to 20 miles per hour. The third one, expensive part, what about the map, right? You use computer vision. Of course, you can do online mapping, but that's very expensive computation-wise. But what about offline maps? So we built this multi-layer map, high-precision visual map using computer vision only. We'll see a demo of it later. So for layer 0, we can use Google Map. We can use OSM. There are a lot of options that we can use. The base level gives you this 1 meter by 1 meter grid. Then you can put a link and notation on it. There's an automation script in our company to do that. So that gives us an accuracy of 1 meter already. Second layer, ground features. If we take a photo here, we project it on the ground using a bird's eye view, and we extract features from it. Then we get a ground feature. Ground feature works best when you are in a, say, city environment like San Francisco, because all the spatial features are noise. You see people, you see cars. But in countryside, you can use spatial feature. You can extract all the spatial features around you to help you localize. On top of it, deep learning, you can extract labels to tell you what kind of vehicle you're gonna encounter, and then what are the traffic signs and so on. So let's look at a small demo of what we have. All right, so one thing I forgot to mention, once you have two cameras in front, and then they're HD cameras, you can use one camera for detection. So you detect, just like the ROI case, you detect there's a person in front of you. You know that's a person, but you don't know how far away the person is away from you. But because we have the ROI, we can extract features from that box. And then, because I have two cameras, I can tell exactly what are the depth of the points within that box, so that I can tell exactly how far away that person is from me. So that's another key feature we have with this design. So that's about a demo, but what about the market? What about technology landing? So we have a lot of customers actually for different categories. The first one is transportation services. What I mean is I'm not gonna put this thing on a, say, Mercedes, and then let Mercedes drive itself here down on Main Street. It's not gonna work. We don't have enough sensors and computing power. But imagine if it's, say, the campus of Berkeley. You don't allow cars to go inside, but you want to do some basic transportation services from point A to point B. That's doable. And then that's a very viable market. That's the last mile problem for transportation. And then that's my belief. So say if you're in downtown Manhattan, there's huge traffic. That's where you want autonomous driving. You don't want autonomous driving on the highway. You want to enjoy driving on the highway. There's no traffic at all. But today we have targeted too much resources on autonomous driving on the highway instead of in the Manhattan scenarios. But if, say, let's close Manhattan. Let's close a small part of Manhattan. Say, don't let human maneuver vehicles go in there, but just let these kind of transportation services go in there to take you from point A to point B. Well, that actually solves the traffic problem. You don't need that many cars to run the whole area of Manhattan. So that's first market, transportation services. Second one, the form factor of a car, you'd say, that's a tank. That's not really a car. Why did you build tank instead? Well, that's the requirement from our customers. They are doing delivery business. So most of the time, when you shop today, you shop online, and then they need to have a team to deliver your product to your home. But if we have this vehicle and put a box on top of it, and then put the camera on top of the box, then you have this form factor for a delivery vehicle. And then exploration vehicles. Say after an earthquake, everything's messed up, and then you don't want to send your rescue crew in there yet. It's too dangerous. This one can go in, explore the environment, capture all the images, and then build a map at real time to tell you where are potential survivors. And then forklift, that's industrial scenario. They can help you moving cargoes within a warehouse. So we already have these customers using this product to perform these scenarios. So I think really autonomous driving is coming. And then to ship this product, we can ship it with a few thousand US$. That's it. We are not shipping a vehicle that's costing, say, $200,000, $3,000. I don't believe in that direction. I don't believe you can ship massive amount of product at that price point. So that's pretty much it for my talk. I have some references here in case you want to dig deeper. We have several papers out. We have a book on autonomous driving. But thank you so much.
Great, thank you very much for that talk. Are there any questions? Okay, they're all in the back. We'll start here.
Thank you very much for the talk. Stereoscopic cameras usually have a lower depth of field than, let's say, LiDAR, for example, or particularly stereoscopic RGB cameras. How are you able to compensate for that if you're primarily using that as sort of the depth sensing sort of
Well, this problem with depth sensor, unless it's a high-end LiDAR, it's not going to go very far. The usual TOF, they have a range of 3 meters or so. But passive cameras like this one, if definition, it's high definition, have enough resolution, you can actually cover a fairly large area.
We have another question.
In the demo, we see that the exploration vehicle is driving in the forest. That means you need to dynamically determine which direction to go without a map. So how do you determine the situation in that case? Thank you.
Well, so when you do any kind of map, there's a step of cleaning up the map. Any data you capture, there are noise, such as other vehicles. So that's based on semantic information. Semantic information captures, say that's a moving car, that's a moving pedestrian, then you take it out from the map. So, but you don't get feature point from there.
I think we have time for one more question. Let's take one from this side.
How accurate is depth perception when using 2 cameras instead of a LiDAR?
Well, that's a very interesting question. So when you use vision, usually it's less than 1% or 0.5% accuracy. That meaning that's a ratio between, say, I'm 10 meters from you. Then you times, say, 0.5% of accuracy. That means your position will shift by a 0.5% accuracy. So the further away the object is, the bigger the noise is. But the closer it is, then the smaller the noise is. Usually the range is 0.5 meter to 50 meter in this configuration. But anything further than 50 meters, then the considerably larger noise.
Great, I'd like to direct further questions to the speaker. You can come up to the podium and ask directly. Thank you very much for your attendance.
All right, thank you.